This is a video of me solving the first problem that we assigned and talked about in class today. I'm going to go through it slowly and in a lot of detail to make sure that we practice with things like our sign conventions and so on. Getting all those right is crucially important and something the book assumes you are already practiced at. Okay, so I know that from this problem I'm going to sketch out the overview of how the solution will go. I know how the solution will go because I have solved the problem. In practice, I would sort of work my way through it, and maybe I'll model this in class sometime. And it might end up a lot messier. Today, it'll be nice and organized. Okay, so we're going to use a free body diagram and Newton's second law in two different directions. We're going to have one free body diagram, but we're going to have Newton's law in the translational direction and Newton's law in the rotational direction. And you can see this because you have translational and rotational motion coupled in this problem. From these two different equations, we'll combine to get a single equation of motion. And that will eliminate the frictional force, which acts here, causes the wheel to roll, and is unknown. Finally, once we've combined these two equations into one, all we'll have to do is do algebra to get them into the form that we want up here with the outputs and inputs and in all the variables that are given here. And EOM are equations of motion. That's the same thing as the mathematical model of this system. Okay, let's begin. So, I'm going to go through Newton's method, referring often to our detailed sign convention process. This is a document I've put on Scholar. It'll be hard to read here in the video, but you can grab a copy and follow along as you watch this video. So I'll be referring to this and pulling it on screen whenever I need it. So the first step in Newton's second method is to draw a free body diagram. We only have a single mass, so we'll only need one free body diagram in this problem. Here it is. It's a circle. It has a mass m and a moment of inertia j. Note that the mass m wasn't given in the problem, so later we'll have to eliminate that as an intermediate variable. But it's okay for now. Step 1 of our detailed sign convention problem says to draw each mass and nearby write Newton's second law, in our case Newton's second laws, making a note defining the positive direction. And I'll show what I mean by this. Nearby the mass here, I'm going to write the translational version of Newton's law. The sum of the forces is equal to the mass of the disk times the acceleration of the center of the mass. And notice that positive x is defined to the right, so I need also positive x double dot defined to the right. And I'll sketch that right here beside my forces. This reminds me which forces are positive when I do Newton's law. Similarly, for summing the torques, I look for a sign convention on theta, and notice that the theta direction is not defined. I'm going to pick it in this direction arbitrarily and make a note of it. I'll mention later where, had you reversed this, all of these signs would be reversed, but later another sign will reverse, so it would still work to pick theta in a different direction. Perhaps theta aligning with the input torque would be another sensible choice, but I'm going to stick with this one. And then over here, noting that theta double dot must be in the same direction as theta up here, I will indicate that just to the right of my summation sign. Okay, that completes step 1 in the sign convention process. Step 2 is the important step. It reads, imagine the mass with positive displacement and moving in the positive velocity. Draw the resistive force of each element on your free body diagram. So here's my mass. I'm going to move it from the 0 point in the positive direction and imagine it's traveling with positive velocity. How will the spring act on this mass? Well, you know that the spring, its resistive force will oppose the positive displacement, and I'll draw the resistive force in that direction. Likewise, the mass has a positive velocity acting to the right, and I want to determine the direction of the frictional force here at the point. Well, if the mass is going in positive direction this way, the frictional force has to oppose that, and so I'll draw the frictional force in this direction. Finally, the input torque is specified. The direction is picked in the problem for positive input torque, so I need to just put that on my free body diagram. There are two other forces acting on this. They're not important. There's the mass times gravity. I'm going to call that the force of gravity acting down. And there's the normal force acting up. And if I wanted to, I could write a third Newton's law. The sum of the forces in the y is equal to the mass times the y acceleration. But since the disk neither moves up or down, the y acceleration is 0. And that equation would simply tell me that the normal force is equal and opposite the gravitational force, which I know to be true. So I'll scratch those off of my free body diagram. Okay. Now, let's write the magnitude of the constitutive element forces. In this case, we have a single spring. So for each force, when you write the constitutive law, determine the signs inside the law such that the element does what the drawing shows. What I mean by that is here's the spring force. We know that the magnitude of the spring force will be k times the displacement of the spring, but will that be positive or negative? Well, I go up to my spring and I imagine fixing one end, which is convenient because it is fixed, and displacing the other end in the positive x direction. If I stretch this spring in the positive x direction, will the force look like this or look opposite? The answer is the force will pull backwards as drawn, so my x needs to enter with a positive sign into this equation. Imagine I had defined x in the opposite direction here, so defining positive x going to the left. Then as I stretched x in the positive direction, which would be compressing the spring would push opposite this force, and in that case I would need a negative sign here. That's not the case in this problem, but that's what I mean by making the spring do what the drawing shows. Okay, now that I've completed that, I'll move over here and begin writing our forces. The final step here says if the force direction drawn in step 2 agrees with Newton's direction, step 1, then include with a positive sign. If it disagrees, use a negative sign. So here is the spring force. It acts this way. Positive forces act to the right, so I need to include the spring force with a negative sign in my Newton's second law. Similarly, positive forces act to the right, the frictional force acts to the left, so I need to put a negative sign here. On the torques, there will be two torques about the center of mass of the disk here. The first torque is the input torque. It acts in this direction positive. That is the opposite direction of what I've defined positive over here, so I need to include the input torque with a negative sign. And then the frictional force times the radius of the disk is a torque in this direction. That direction agrees with the positive direction here, so I put a positive sign on that. This completes writing my two Newton's second law equations, and I've established my sign convention and been consistent throughout. Now I need to combine these two equations to eliminate the force of friction. You can choose which one you solve for the force of friction and plug into the other one. It doesn't particularly matter. I'll arbitrarily choose to solve over here for the force of friction. So the negative force of friction equals mx double dot plus kx. That move that kx to the side. And then I will negate the whole equation. And I've solved for the force of friction as a function of the other variables. I'm going to take that and plug it in right here to get my combined equation, negative Tn plus r times negative mx double dot minus kx equals j theta double dot. This is my equation of motion, but I still have a lot of unknowns. So I need to apply algebra to get my equations of motion in the correct form. The first thing that's bothering me is that I have x's and thetas. This is rotational motion over here, and this is translational motion in the x. And the link between those two, as we discussed in class, comes from the arc length formula. S equals r theta. That's the generic formula. And I'm going to determine how to apply that to this problem. In this problem, what I'm talking about arc length is the movement of the center here, and the rotational is the rotation of the wheel, and so which radius? And so if I want to displace, say, a meter in the x, I need an equivalent rotation of theta in the positive theta direction times the radius r. That's my application of the arc length formula to my physical problem, and it looks very similar, and it always will. Notice that had I defined positive theta differently up here, that positive x would have been a negative theta. Imagine positive theta going in the counterclockwise direction. Positive x would correspond to a negative theta, and over here I would have written a negative sign. My arc length swept out, positive x, would have corresponded to a negative theta. It might make sense to call this theta arc length, just to indicate that this is the ideal theta from the arc length formula, and this is the actual theta from my problem. Good. The other thing to remember about this is that I can differentiate it, and since the r is constant, I'll get that x dot is equal to r theta dot, and x double dot is equal to r theta double dot. Over here, I'd like to eliminate theta from my problem because my output is x. So I can solve this for theta double dot, like so. And we'll plug that in here to our equation of motion. And now we've eliminated theta from the problem. The next thing that I want to eliminate, and the last thing, is this intermediate variable m. So this is the mass of the disk, which was not given. And to find the mass, I need to know that the moment of inertia of a rolling disk has a formula in terms of the mass and its radius. If you didn't remember the moment of inertia of a disk, you would go look this up from a table. There's a small one in your textbook, or you can use any one online. The formula that's correct is 1/2 mr squared. This is the rotational formula for a disk rolling about its centroidal axis. And I can use this to solve for m as a function of j, so m is equal to 2j divided by r squared. Take that and plug it in over here on the right. Maybe I should draw arrows here to indicate here and here. You get negative Tn plus r negative, plug in that 2j divided by r squared, x double dot minus kx equals jx double dot divided by r. Okay, and I've actually completed the problem. I'm going to do some algebra just to get it into a better looking form. I would like to get all my x's and x dots collected and on the left-hand side, and get all of my inputs onto the right-hand side. So I'll just do the algebra steps here one by one. I'll move the torque over and move this over. So I'll have r negative 2j over r squared x double dot minus kx minus jx double dot over r equals, move the torque over, positive Tn. And then I don't like this r in the denominator here, so I'm going to multiply both sides of the equation by r. R squared negative 2j over r squared x double dot minus kx minus, so multiply by r here cancels, jx double dot equals rtn. I want to combine, let me just do the algebra to simplify these equations. So this r distributes here, and I have negative 2jx double dot, r cancels there, minus r squared kx minus jx double dot equals rtn. And then I would like these terms to be positive, so I'll multiply the whole equation by negative 1, 2jx double dot plus r squared kx plus jx double dot equals negative rtn. And finally, I'll combine the x double dot terms to get this in the format that we're most familiar with. 3j x double dot plus kr squared x equals negative rtn. This is the mathematical model of the system. This is the equation of motion. Note that all of my outputs are on the left-hand side, and my inputs are on the right-hand side, and this is how I like things. To find the unforced natural frequency, I need to get into the standard form that we're used to. The standard form of a second-order equation is x double dot plus omega natural squared x equals 0. And to make this look like that, unforced means that the input torque goes to 0. You'll see that all I need to do is divide the problem by 3j. So x double dot plus k r squared divided by 3j x equals negative r divided by 3j tn, but tn goes to 0 in the unforced case. This looks like this, and I can read off directly that the natural frequency is the square root of k r squared over 3j. This completes the problem. Let's connect back to the overview and indicate all of the steps. So how did I start the problem? I drew a free body diagram, and I applied Newton's second method very carefully with my sign convention process to make sure that I get these two equations. I then combined those two to eliminate the frictional force. That was done here. And from that point, all I did was algebra. I plugged in the translational to rotational link here, and I plugged in the mass and rotational moment of inertia here, and then just did algebra to get to the final answer. The final answer was the equation of motion. The second question was about the unforced natural frequency. So I zeroed the input and rewrote in a form that we can read the natural frequency off of here. This completes the problem.